Okay, welcome back. Happy Friday, everybody. Today is lesson number 25. This is a supplemental section, meaning it is not specifically in your textbook. We're going to talk about polynomial models and polynomial regression. You'll remember a few classes ago we talked about linear regression. That was where we had a bunch of data points and we would try to find the best line, the line that was closest to all the points. This is something the calculator or computer can do for us, and then we interpreted the results. So instead of taking the data points and trying to find the best fit line, maybe we try to find the best fit parabola or the best fit cubic graph or something more complicated. So that's what we're after today. Just looking ahead, project number 3 is due on November 14, which is a week from this coming Monday. Okay, 1 week from Monday. Did everybody get a copy of the project? I gave it out last class. Got it? Okay. All right, so coming back here to page 16, let's just flash up the answers here to this first question, the matching one. This guy right here, part A, what degree do we think? Again, page 16. Yeah, this is a 4th degree, maybe, right? I mean, it's got a turning point at the top, another turning point at the bottom, and one more turning point at the top, so that's 3 turning points. And we know the degree is maybe 1 more than the number of turning points. So if that's a degree 4, well, yeah, and it's down, right? So unfortunately, there are 2 degree 4s here, the number 4 and number 5. But we know that if it's positive, both are up, and if it's negative, both ends are down. So this one is 5, right? Negative. Good. Okay, just while the other degree 4 one is in my brain, let's identify that. Where's the other one that's a degree 4? Is F, right? Kind of the same idea, but both ends opening up. Okay, so this one down here must be 4. Okay, the next one, part B, what degree? Looks like a degree 3 because of the 2 turning points or the 1, 2, and 3 x-intercepts. So we're looking for a cubic. I see a cubic in number 2 and also in number 3. So remember the sign, the leading sign determines what happens at the far right. The leading sign always matches what happens at the far right. Positive leading sign goes up to positive infinity. Negative leading sign down to negative infinity. This graph in part B goes up to positive infinity. So which one are we picking? We got to pick 3, right? Because it's got the positive x cubed. X cubed is still on my brain. Where's the other cubic one? There's part C. And this one you can see at the far right goes down. So it must have had a negative leading coefficient. So that must be number 2. Okay, part D, what degree? Probably a 2nd degree, right? This looks like a parabola over there. So I think there's only one of those. It's a 1. The fact that it's a positive x squared, how does that agree with the behavior? Up on both sides, right? Okay, and then finally E, all right, process of elimination. It's got to be 6. All right, let's count the degree. 1, 2, 3, 4 turning points, so maybe a 5th degree polynomial, right? And so 5th degree, hey, that matches, and at the far right, should it go up or down according to the equation? Up to positive infinity because it's a positive x to the 5th. Okay, I'm buying it. We're good on the matching? Okay, so we're not going to go over the rest of this, but we are going to jump to the next page with the demo. So middle of page 17 is where we are. Number 1, we now move on to polynomial regression. Earlier this semester, we entered data into our calculators or into GeoGebra and performed linear regression. Now we'll see what to do if the data is not very linear. So at the outset here, I'm going to say, I'm not going to pass out graphing calculators today. You're not going to have to do any button pushing today. We're not even going to talk about what the steps are for coming up with the best fit parabola equation. It's quite similar to what we did with the linear stuff. So what I'm far more interested in is that if I just give you the equation, that you can interpret the results. Or you can look at a bunch of data points and say, hey, a line doesn't look so good there. Maybe a parabola or maybe a cubic or something like that. Okay? All right, so let's take a look at number 2. The table below shows the number of women in the full-time civilian labor force in millions with children under the age of 6 for selected years. All right, that's a mouthful. Let's take a look at the data here. So in 1975, the number of women in the workforce with at least 1 child under the age of 6 was 4.851 what? Million, right? Millions of women. So about 4.8 million women in the workforce had a child under the age of 6. 5 years later, 1980, we were up to 5.88 million women with a child under the age of 6, and you can see increasing the whole time here, right? But not necessarily increasing in a linear fashion. You can see the data points here are these black dots. And, you know, it's looking pretty straight here for the first part of this chart, but then at the end, it actually like almost looks like it's leveled off here, right? You see that? I mean, like these two, yeah, it's a very slight difference. It only goes up by like 0.15 or something like that, million women. Okay, so the red thing right there, that's the line of best fit. That's old for us. The equation is given there in red, y equals 0.211x, etc. But the brand new thing is that maybe we can capture this sort of leveling off trend with something more complicated than a line, because the line just keeps going over a certain amount and up exactly the same thing, right? Over one, up the slope, over one, up the slope. Whereas a parabola can have a changing rate of change. And what do you think? That blue parabola, it you know, like it's going up and it's pretty darn close to these points, and it starts to curve around and get that last one, which was sort of the one that was kind of an outlier before. And we know parabola equations are going to have x squared. This one is going to be negative x squared because it's down. So there's the equation. It's actually missing the y equals negative 0.0048x squared plus some stuff. Okay? All right. So let's write down our two equations. Or if you're lazy like me, we're just going to kind of put some arrows here. So that's the equation of the regression line. And then the other guy with the y equals is the equation of the regression parabola, okay? Okay, so you're all going to turn to the next page. I'm going to keep these two things here so we have the equations in front of us. But on the next page, it says, use the linear and parabolic models to predict the number of women who are working with children below the age of 6 in 2011, and then which model seems like a better predictor. Okay, so 2011. First, we got to translate. You can't just plug in 2011 for X because years since 1970, right? So that's our first translation. So this means 2011 corresponds to what X? 41 is good, right? 41 years since 2011. So what you are going to do, probably with the assistance of a calculator, is plug in 41 for X in the line and 41 for X in the parabola. I'm going to grab some other calculators in case people don't have, so that everybody's doing something, but let's see if we can plug into both.